Hey guys, so Isabel and I will be explaining limits. In this video, I will be explaining limits, rates, and tangents. A limit can be described as when a x value is approached, there is a y value that is being approached. For example, in this graph, we can see that when the x value approaches 1, the y value approaches 1. So 1 would be the limit here. And when x approaches 2, the limit is 4. And when x approaches 3, the limit is 9. A limit can also be described as the slope of a tangent line. If we have a look at this graph here, we can see that at this point, this red line is called the tangent line. The tangent line here only touches this one point on the graph. If we take any other point on this graph and connect it to the original point, these lines would be called the secant lines. As the points get closer to the original point, we can see that the secant lines get closer to the slope of the tangent line. As the points get closer to the original point, we can see that we are getting closer to the limit. This graph is also a distance versus time graph and should give us the average velocity. The instantaneous velocity at this point would be the distance in distance over the difference in time. The average velocity over a very small time is very close to the instantaneous velocity. To find the instantaneous velocity at this point, we would find the slope of the tangent line, which is also the limit at this point in time. As well as velocity, limits relate to all rates of change, including the infection rate of an epidemic, the newly infected individuals per month, inflation rate, change in consumer price index per year, and the rate of change of atmospheric temperature with respect to altitude. So our first example is a wrench released from a state of rest at time t equals 0 travels a distance s of t is equal to 4.9 t squared meters in t seconds. Estimate the instantaneous velocity at t is equal to 3. The first step of this question is to pick small intervals from before t was equal to 3 and from when t was equal to after 3. We would then apply these intervals into this equation. For example, for the first interval, it would be 4.9 multiplied by 2.8 squared minus 4.9 multiplied by 2.7 squared, all divided by 2.8 minus 2. These would be the average velocities that we would get after plugging everything into this formula. From when t equals 2.7 to 3, we can see that the average velocity is increasing, but when 3 to 3.2, the average velocity still increases. But at 3, we can see that the average velocity is between 28.91 and 29.89. Therefore, we can see that the instantaneous velocity at t is equal to 3 is 29.4 meters per second. Our next example is a stone is tossed vertically into the air from ground level with an initial velocity of 15 meters per second. Its height at time t is h of t is equal to 15t minus 4.9 t squared meters. Compute the stone's average velocity over the time interval 0.5 to 2.5. Like for the question above, we use this formula, h of t1 minus h of t2 over t1 minus t2. t1 would be 2.5 and t2 would be 0.5. So then our equation would be 15 multiplied by 2.5 minus 4.9 multiplied by 2.5 squared minus 15 multiplied by 0.5 minus 4.9 multiplied by 0.5 squared, all divided by 2.5 minus 0.5, which should give us 0.3 meters per second. This example is the part B of the question we did previously. Compute the stone's average velocity over the time intervals 1 to 1.01, 1 to 1.0001, 0.99 to 1, 0.999 to 1, 0.9999 to 1, and then estimate the instantaneous velocity at t is equal to 1. Which is also equal to the instantaneous velocity at t is equal to 1. Sorry, all of the instruction for this video just got cut out. Using the previous method, we can find the average velocity at each of these intervals. As the intervals approach 1, we can see that the average velocity approaches 5.2, which is also the instantaneous velocity at t is equal to 1. And this example summarizes how to find the limits for rates of change questions.